All right, I think in the interest of time, we're going to get going, and I think people will be able to catch up as they join in the next couple of minutes. Wanted to thank everyone for joining us for the webinar today. I'm Colin Rowan with Pecan Street, and I'm going to be the moderator for the discussion today. I'm going to make some very quick introductions and announcements, and then I'll pass the mic to Scott Hinson, who's the Chief Technology Officer at Pecan Street, and he's our first speaker. He is going to be followed by Greg Ledva, who's the Director of Emerging Technologies at Virtual Peaker, which if you follow distributed energy and demand response, Virtual Peaker might be the most perfectly clear and accurate company name ever selected. So hats off to your branding department. Greg's going to be followed by Johanna Mathieu, an Associate Professor of Electrical Engineering and Computer Science at the University of Michigan. Johanna will share some insights of research she's conducting with Pecan Street regarding air conditioning systems and load management. But before we get started, just some quick housekeeping items. We're going to be monitoring audience questions throughout the webinar. We do that through the chat function in Zoom. So if you have a comment or a question or feedback or need clarity on something, please enter that in the chat function. I and Josie with Pecan Street are going to be monitoring that, and we'll be trying to filter those questions into the discussion. If you're not already on the distribution list for Pecan Street events or press releases or blog posts and you'd like to be, please email me at media@pecanstreet.org. You can find our announcements and blog posts at pecanstreet.org/news, and you can find all of our upcoming webinars and events at pecanstreet.org/events. And with that, I am ready to turn things over to Scott. I'm going to be working Scott's slides right now. So Scott, if you want to get started, I'm going to go ahead and switch over to your slide deck, and we will get ready to go.
Well, thank you everyone for attending today. As Colin mentioned, I am the CTO of Pecan Street. I'm going to give a real quick overview of Pecan Street because my guess is most of you know who we are. We're a 501c3 nonprofit based in Austin, Texas. We have a number of research verticals. You can see them here: energy, water, transportation. We've also added soils research to our mix. Next slide, Colin. On the energy side of things, we like to do field research. We have a great test bed set up where we have installed instrumentation behind the meter for the utility meter for electricity, and we get a bunch more information than a utility meter would get on a single home. And that gives us the ability to do these sorts of programs that we're going to talk about today and provide information to the researchers that would otherwise be unavailable. All sorts of fun, fancy math can be done with the types of information that we get. At this point, we're collecting in upwards of 7 billion plus data points daily. We have test beds in Austin, Northern California, upstate New York, opening test beds in Puerto Rico and Detroit, as well as Delaware this summer. And so we've got a number of different places where we can do this kind of research. Next slide, Colin. So the data that we collect looks a little bit like this. This is actually the 1-minute version of the data and only one parameter that we measure. This is real power for the electrical engineers in the group, in the audience. We also collect apparent power, current THD, voltage, phase angle between voltage and current RMS, and we do that at 1 second intervals. So we get power quality type measurements on every single circuit in the home, or as many circuits as we can grab. We aim to get every single circuit, but we don't always get them all. And so the data that we actually have available is far more granular than even this graph shows. All right, next slide. So a little bit of context as to why we think projects like this are absolutely critical. With the increased penetration of renewable energy sources on the grid, we're sort of having to change the paradigm of grid operations. What used to be generation following load is going to have to, at least in some manner, change to load following generation. The exact mix is yet to be determined. A lot of this is being driven by, frankly, by cost, right? There's been a number of incentive programs over the years that have gotten research going, and you can see some of these pricing curves on this plot. I pulled a lot of these from our world and data and some existing reports. So, batteries have plummeted from, the first battery system that we got at Pecan Street was $60,000, and it had less energy storage than what you're getting for 10 grand commercially available, and we had to custom make it. The price of solar and wind energy sources is now below gas and coal, and it shows no sign of heading the opposite direction, especially since natural gas prices are increasing. And then the last curve, this one's sort of an odd one on the far right there to sort of understand, but basically, I need to update this. Historically, we've been really bad at predicting the penetration of renewable energy sources. This example is PV, and what they're showing is the different predictions over the years, and then the actual adoption curve. And every year they go, oh, we missed by a lot, and they make a new prediction, and they say, okay, well, surely that rate won't keep up, and it actually accelerated. And this has continued. This pattern has continued. All right, next slide. So you can see that in Texas, where we are located, what this means is that the mix of new generation sources being requested or being bid into the ERCOT market is such that renewables and energy storage are clearly winning. Right now, there is zero coal being bid into the ERCOT market. Absolutely none. That is zero. And then batteries alone are, if I remember correctly, this is sort of pseudo blocked for me. If I remember correctly, yeah, batteries alone are double the amount, or more than double the amount of natural gas being currently bid. Now, not all of these projects, this is like more than an ERCOT's worth of energy generation. Not all of these projects are actually going to make it, right? Only a percentage of the ones that even get interconnection agreements actually get constructed and built. But you can see the clear trend that solar batteries and natural gas are beating, or solar batteries and wind are beating natural gas. Next slide. So that brings me to sort of the topic at hand. And I'm again going to use the ERCOT market as sort of the example. To lesser extent in some areas, or greater extent in some areas, these things are happening all over the country. Just yesterday or day before, there was an ERCOT webinar around aggregated load resources, ALRs, and I highlighted the critical point. The rules have been established in ERCOT for a while, but they market mechanisms and the participation requirements for aggregated load resources in ERCOT are so onerous that there are none registered in the ERCOT marketplace right now. And compare that to what we're seeing on a nodal pricing, which is the map on the right. This is one of the more extreme examples of pricing disparity I've ever seen in the state of Texas. And you can see where, and this was a very short-lived event, an hour or so before things got a lot closer in pricing. But in the nodal market in Texas, at one point, the price in the Houston area was roughly $3,000 a megawatt, which translates to $3 a kilowatt hour. Retail prices for consumer electricity in Texas is 12 to 15 cents a kilowatt hour. So you can see where if you had to buy energy on the nodal market at that time, that was a money losing proposition for you. If you had energy available, you could make a lot of money. But just down the road, the price was negative 2,000. And this was brought about by transmission constraints, coal power plant fire. So there was a coal power generation unit knocked offline, And these sorts of events are more and more frequent, and with climate change are going to become more and more frequent, and the need for controlling load and doing it smartly is pretty high. And with that, I'm going to turn it over.
All right, thanks, Scott. One quick point that I thought maybe you could add to before we switch screen sharing to Greg. We've talked recently internally at Pecan Street about really what the opportunity and the scale and the scope and the importance of load shedding is. What kind of management or percentage would have made a difference in that Houston area for that map that you showed?
So the catch is that the way the market is set up in Texas as a scarcity market, right? As you start to run out, prices skyrocket quickly. And you don't need to shift that much. A few percentage points of reduction in terms of overall load is enough to be a big impact on that pricing structure that we just saw. So you don't always have to move a lot.
Got it. Awesome. All right, Greg. I think we're ready for you as you cue your slides up. I'll just give a quick introduction. So we asked Greg to go second in this to kind of give a general lay of the land of this kind of, load shaving potential, what it is, what his company does, and how, it kind of puts the project that Pecan Street and Johanna have been working on in a little bit of context. So Greg, I'll pass the screen to you.
Perfect. Can you hear me? Can you see the slides? Are we?
Yep, we're good.
Perfect. So yeah, my name's Greg. I am from Virtual Peaker. I am the Director of Emerging Technologies. I'm going to talk briefly about who we are and what we do before Johanna goes into the project. And then I'll go a little bit more into industry concerns, adoption, things around adoption, and stuff like that after she chats a little bit about the project. So for some background, I've been doing distributed resource control for about 10 years, mostly in academia. Started with Virtual Peaker over a year ago. And what I'm doing here is a lot of algorithm development, analytics, a little bit of software development, and things like that, all supporting the general capabilities of Virtual Peaker. So who is Virtual Peaker? Who are Virtual Peaker? What is Virtual Peaker? We're a software company that provides software solutions to utilities, could be aggregators, folks interested in controlling distributed energy resources. We are headquartered in Louisville, Kentucky. We've switched to remote first, and to give you some scale of the maturity of the company, we raised about $16 million in the Series A earlier this year, and have roughly 50 employees, just to give you some idea of where we are as a company. The platform is basically a software platform with a few different areas. We have a DERM suite called Shift, provides device control, behavioral demand response, reporting and analytics, things like that. We have an engagement suite, which allows you to interface with customers, messaging, incentive delivery, device management. And we have a forecasting suite that provides forecasts at different levels, like system load or further down, and provides it over short, medium, and long-term forecasts. So this is essentially the software platform. We'll be talking mainly about the DERM suite in the context of peak shaving. So we have a bunch of smart thermostat integrations. The general control approach that's common with these thermostat integrations is temperature offsets. And we'll go into more about how that impacts the end users, but Part of this is the limitations in API and kind of what they're willing to let us do. And so we have utilities across the country that we're working with, programs of different sizes, but all in all, it's mainly aimed at peak shaving, which directly addresses what Scott was talking about in terms of reducing and shifting load across time periods to help mitigate price excursions. And the events are basically just based on a temperature offset from what the homeowner sets. And so it's fairly directly impacting their comfort level in terms of what they want to be happening and what is actually happening. And so just providing a little bit of background on what we're doing. And then I'll kick it over to Johanna to talk about the project and then talk about more in terms of how the project impacts potential technology in industry.
Awesome. All right. Thank you, Greg. Real quick, just the communication person here thinking about kind of stepping back for a second. Cost is a significant issue with constraints. There are a number of reasons why we're focused on it at Pecan Street, and I think why a lot of people who are on the webinar might be. Cost, of course, is important. Overall congestion on the grid, it's kind of hard to read anything about the electric grid these days without hearing about resilience and hardening the grid and preparing it, not just with hardware, but also with intelligent software that can manage it better is hugely important. And then, of course, all of this specifically for groups like Pecan Street who are climate focused, has the goal of reducing the amount of fossil fuels we need to have on the grid and increasing the amount of renewable, non-emission electricity we can have on the grid. So all of these come together for an important objective. If you live anywhere near Texas, air conditioning, this might be a good segue for Johanna. If you live anywhere near Texas, air conditioning is just an incredible driver of energy use. The largest driver of energy use in Texas, unless you have an electric vehicle. And so whether you're in Texas or other states, heating and cooling is a big focus, not just on overall energy use, but on how we can optimize heating and cooling behavior to make things easier on the grid. So we'll pass it over to Johanna now to talk about the research that we've been doing and how that might be applicable in the heating and cooling space. Johanna, it's all yours.
Great. Thank you so much. You can see my slides, okay?
Yes.
Great. So I'm riffing a little bit on the presentation we just gave last week at Distributech that Scott gave for our project. So some of these slides are from there. But what I want to highlight for you is what we're doing here is trying to move from load shedding to load shaping. So instead of just reducing load, can we shape the load to help the grid? And instead of doing temperature set point control, like Greg was mentioning, can we do non-disruptive on-off controls so people don't notice impacts in their house based on how the temperature might change, only small amounts. So our project that we're all, most of us are involved in here is a collaboration between University of Michigan, which is leading the project, Los Alamos National Lab, University of California, Berkeley, and Pecan Street, and it's funded by ARPA-E. It's a grant from the ARPA-E Open Program from 2018, and we're wrapping up the project this year. So the main idea is we want to coordinate electric loads to shape the load, that shape their power consumption in time. And so we do that through a feedback controller. The types of loads that we're interested in using are things like air conditioners, but also water heaters and refrigerators. We can use a controller to control them to basically make their power consumption track a signal. So if you've looked at control problems before, this is sort of a classical control problem of how do you get something in aggregate to track a signal. But what that actually looks like here is if you don't control the loads, they might consume power over time that evolves according to this blue line, but you prefer them to sort of track this balancing signal, which is the black line, and then we control them in a way that gets their aggregate power to follow that black line as best as possible. So we're primarily interested in thermostatically controlled loads. The acronym that we commonly use is TCL. So forgive me if I use that occasionally in the talk to talk about air conditioners, but an air conditioner is a type of thermostatically controlled load. It has a local thermostat, and they're very useful loads to use because they sort of store thermal energy, and you can almost think of them as like thermal batteries. So how does this work? I mentioned we're doing on-off control, not temperature set point control. So I'm just going to walk you a little bit through how an air conditioner actually works. This is showing the different states that the air conditioner can have. So this is the temperature of your house, and this is if the compressor for your air conditioner is on or off. And so I'm going to show you here, as it's operating within this range, how it consumes power over time. So first, your room might heat up, then you flip on your air conditioner. Actually, the thermostat in the air conditioner does that for you. And then it cools down your space, and then it flips itself off. And it keeps doing that over and over. So the power it consumes is in these little pulses that look like that. So what our control does is, instead of changing the temperature set point, which could make you feel too cold or too hot, what we're going to do is keep the temperature between this lower edge of the band and the upper edge, but flip the air conditioner on and off at slightly different times. So it might look like this, where your room is sort of heating up, and then maybe there's a big injection of solar PV in the grid, or a big injection of wind power in the grid, and we actually want to increase the power consumption of the grid. So we're going to switch on your air conditioner just a little bit early, and then use the air conditioner to cool you down. And then maybe that wind or solar goes away, and so we want to switch it off a little early. So you get a pulse that looks a little bit different down here versus over here, and these pulses can all have different durations to them, and so it's irregular. But if you now stack up thousands of air conditioners together and you're controlling them in this sort of way, so they're all sort of switching on and off at slightly different times, you can use that to smoothly track a power signal, like I showed on the previous slide. So how is this project we're doing different? There's actually been a lot of research on load control, demos, pilots, academic studies, hundreds of thousands of papers published. But our question when we started this project was, if there's lots of work on it, why isn't load coordination common practice across this country? And we postulated that we haven't established sufficient credibility for this yet, especially at scale, because there's a lot of potential technical issues that could arise when you coordinate loads. And there's been pushback from the industry. We don't want to try this yet because we haven't worked out these technical kinks. And I'll talk a little bit more about what those look like in a second. So our overall goal for our project is to try to resolve these technical obstacles to show that when you coordinate loads at scale, you can do it in a way that provides lots of benefit and hopefully no detriment at all. So the technical issues that I mentioned, so there's a concern that while you're shaping the load, maybe you're helping balance supply and demand, but you're causing local issues in distribution networks. So that's one potential issue. Another issue is you're controlling resources across communication networks, which are not perfect, and there's delays, lost information. Could that cause the control you're doing to sort of backfire, and then you're not actually controlling them how you want them to, and so you're actually causing more harm than good? And the last point sort of is related to that is maybe you're controlling them in a way that ends up synchronizing them, and then they end up turning on and off all at the same time, and that actually causes like voltage to go on and up and down at the same time, which is also not good for the grid. So the question is, do existing controllers do that? How can we avoid those things? So we're trying to develop a solution that's network aware, communication constrained, with stability guarantees, to be able to coordinate aggregations of air conditioners, shape their load. Specifically, we're trying to show that they can provide frequency regulation. And we're trying to show that you can do that in a way that's technically feasible, effective, low cost, and so on. So why are we doing frequency regulation? Frequency regulation is where resources increase or decrease power consumption or production very quickly to balance the grid. It's not necessarily maybe the best service that you might want to provide, because there's actually only a small amount of frequency regulation that grids need, and that service is usually covered by hydro and natural gas power plants and so forth. But it's one of the technically most challenging services you can do. So if we can demonstrate this with aggregations of loads, we basically can use them to do any kind of load shaping. Sorry, just time check here. So what is our approach? We developed a simulation testbed where we have very high fidelity simulation models of both air conditioners, houses, the distribution network, and the communication network. We're developing an experimental test bed with 20 real air conditioners in the lab at Los Alamos National Laboratory. And then we have the field test bed at Pecan Street with 100 real houses that each have air conditioners that we're controlling. We're using the field testbed data to validate the simulation testbed and the experimental testbed. We're also using the findings from the experimental testbed testing to make sure our simulation captures all the effects that we see. We're coupling the simulation testbed and the experimental testbed so that we can coordinate large populations of both simulated and virtual loads at the same time. Because 20 air conditioners is not enough to show large impacts, but if we can couple those with virtual ones as well, we can show larger impacts across the network. And we're also doing the coupling here where we're coupling the 100 real ones with simulated ones so we can show how this scales across networks. So just a few more slides very briefly, just to show you some pictures. This is our actual picture of our experimental testbed at Los Alamos National Lab. There's a huge warehouse that has these boxes in them, and each box is a room, which is basically modeling a house, and each house has an air conditioner. And we're actually sending control signals to these air conditioners and coordinating them together with the simulated ones to provide frequency regulation. We're looking at a variety of different controllers. We have identified a variety of different promising controllers. We have some of our own, like the Markov model controller we've developed in past work, but we're also teamed up with Packetized Energy, which is a company based out of Vermont, which was recently bought by Energy Hub, and they have a different type of controller that we're exploring. We've tried to understand if you just use these controllers out of the box, what problems they could cause, and then how to avoid those problems. And so most of our work is trying to extend these existing controllers in ways that mitigate any issues that arise on the distribution network, through the communication network issues and so forth. So we're coming up with extensions to controllers and new controller models. And so that's kind of the innovation, the academic innovation that's part of our work, where in the end we'll have new control designs. And then lastly, this is the slide just showing the installations we're doing for the field testbed at houses in Texas, and some details about what's going into people's houses. Basically, we're installing this custom-made board, which has our hardware software on it. And when I say ours, I mean Pecan Street. So in summary, our goal is really to establish credibility for load control at scale. We're using these 3 test beds which work in concert with each other. And by actually working on these physical devices, we understand what works and what doesn't, so we can fix the things that don't work. And then our sort of contribution here is all these novel controller designs. So I'll stop there and we can proceed back to Greg, I believe.
Awesome, thank you. Real quick, Greg, before you jump in with some commentary, I'll just remind everyone we're monitoring the chat. So if you have a question or a comment or need clarity on anything, don't hesitate to send us a message on the chat. We'll kick it off. I'll send it back to Greg, and then we'll have some Q&A.
Yeah, so just wanted to add some commentary on the project and kind of what I'm seeing going on, and basically some things that still kind of need to be addressed, but overall, a lot of the benefits. One thing in terms of talking about frequency regulation, where we're increasingly talking to utilities less about discrete events and more about how do we continually think about adjusting this load to address their various concerns. And one of the other things that's continuing to pop up is usage of loads to address multiple use cases simultaneously, which requires a lot more fine tuning. And so overall, the frequency regulation control aspect of it, like Johanna was saying, if you can control on those timescales, you can do a lot of other things. And I think it falls under the umbrella of a lot of what people are starting to talk about and think more heavily about, along with a lot of the practical implications of stability and communication constraints and things of that nature, really just lowering the barriers and making people more confident that this will work. It won't cause problems within the system. Overall, I see a lot of benefits to it. Besides that, some of the things I wanted to bring about is there's this classical thought of on-off control in industry, which was historically have a bunch of air conditioners within a program. It's a hot day, turn off a bunch of households' air conditioners for a few hours. The utilities use a benefit. A lot of the homeowners are in a house that's really hot and they're very grumpy, which means that they're probably going to opt out of the program or do whatever they can to avoid that. One distinction I really want to make about the project is it's a more modern take on-off control, and that the thermostat itself is overriding control suggestions, we'll call them, to really make sure that the homeowners are comfortable. And so there are a lot of implications in terms of people continuing to stay in the program because they're basically unaware of things happening. And I think that's a huge benefit as to where things could go. Conversations with utilities, temperature set point changes are something that customers and homeowners definitely see and are not always happy about. And so the more we can move away from that to something that's more non-disruptive, I think is a huge benefit. One of the aspects is API limitation. So as Johanna mentioned, they built a lot of custom hardware for this project, and it was basically because the control capabilities weren't available through a lot of the smart thermostat APIs. And so there needs to be a little bit of action in terms of what information and capability is commonly available through these thermostats, mainly in the sense of, the thermostat itself can protect end users, but allowing some ability on top of that. And I understand from the thermostat perspective that they want to protect user comfort and the owner experience, but at the same time, loosening up that I think would go a huge way towards allowing this type of advanced control. Basically, device concerns. So on-off switching, a lot of people are hesitant about that with air conditioners because they're not sure if it's going to wear out the air conditioner compressor more quickly. But I also know that there are a lot of algorithmic approaches to limit that. And so I don't necessarily think it's a huge issue in practice if you address it. And I think it's very addressable. And the last thing kind of that's going to help enhance the adoption of this, I think, is air conditioners and central air units increasingly have communication capability between the internal unit and the external unit in the household. And this is really beneficial for the power measurement side of things. Right now, communicating with a smart thermostat, there's no real way to understand what the actual power draw of the conditioning device is. But if you've got this communication capability within the air conditioner unit, you could also communicate it outside of the air conditioner unit. And so I think a lot of those benefits really help make this more widely adoptable. And I think people are definitely interested in it. I've heard people be excited about on-off control, the way that Johanna frames it. And so I think things are really moving in a great direction for this to be adopted. And I would like to continue trying to help develop it and see where we can take it.
Thanks, Greg. We're getting a couple of questions here in the chat, so I'm going to get to those in just a second. But I wanted to just ask a general thing. In one of our internal conversations at Pecan Street in the last couple of weeks, we've been looking at kind of what has happened as a result of COVID and stay at home and people's behavioral changes. And one of the things that we've noticed is that people's set points are lower. I kind of admitted I'm guilty of that. I always tried to shave. I always tried to be a little warmer in the afternoon than I wanted to be. And I've just kind of said, you know what, if it's 4 o'clock and I'm going to be working, I'm going to be cool. And so I think there are, to your point, Greg, about kind of, there used to be thinking that if we could get people to have conservation minded set points, that they could set it and forget it. And I think what we've seen in COVID is that people can reset it and forget it. And that's not necessarily a good thing. So this idea of more dynamic control, I think seems promising. A couple of questions, and you hit one. There was a question about whether increased cycling on off would be a problem for motors and compressors and things like that. So I wanted to just give, and you mentioned that you weren't concerned about it, but Scott or Johanna, if there's any additional commentary you wanted to add on kind of the wear and tear on the household infrastructure.
Yeah, so I mean, one of the things that we spent a lot of time, and we're still sort of watching and making sure that we understand, is the impact to the hardware itself. I mean, that every homeowner's fear in Texas is an air conditioning failing, right? It is the forefront of your mind because A, your house is going to be miserable, and B, they're really expensive. And so we have a ton of rules in the system around things that would cause more immediate damage and degradation. Something that you can do that's pretty hard on an air conditioner is called short cycling, where the air conditioner turns off and you immediately attempt to turn it back on. There's all sorts of action between the compressed gases and the compressor that you just don't want to do that. So we have all sorts of rules around that. We also have rules around how often actions can be taken in order to minimize the total on-off cycles. And then the other thing to sort of keep in mind is years ago, we had some researchers, excuse me, at UT look at sizing an air conditioner. And they found that it was very difficult to get an air conditioner right size. They were either oversized or they were undersized. So the air conditioner would either run for hours at a time or cycle itself fairly regularly. And the average number of cycles in a day for an air conditioner in our test bed in Texas was somewhere in the 50 to 60 range. And so there's a number, so it's every half hour or so the thing's, on off. And if you do these sorts of control mechanisms properly, I don't think we have to add to that in a substantial way. So that would be my commentary on that.
Yeah, and just to add to that, there was a question about rapid cycling. Our controls prevent against rapid cycling. Like Scott mentioned, you want to avoid short cycling. There's the lockout period where the compressor has to stay off for 3 minutes or something before you can switch it on again. And so because a single load isn't trying to track the trajectory, provide the full service, but you're doing it in aggregation with thousands of them, right? Each of them is only switching slightly more than usual. It's not a huge impact on that one, but they're working together. So in aggregate, you see these changes in consumption different from what they would be doing if they weren't coordinated. And that's kind of the power in doing this. But we absolutely do not want to short cycle them or switch them rapidly. But you're right that there would be a slight increase in the amount of switching. You could actually reduce that issue if you increase the size of their temperature deadband. So increase this like zone over which you can control them. But it's a trade-off because then people might notice the temperature swings a bit more.
Another quick question. Someone asked about, are we looking at residential only or commercial? And they said that, K through 12 schools or commercial buildings might have real opportunity for here. So I know we're focused on residential for this study, but if you maybe could comment on the potential on commercial, industrial, and institutional users.
Yeah, the dynamics I showed you for the air conditioner switching on and off, that's typical in residential in the US. It's HVAC systems in schools and commercial buildings are different, right? And they're also variable speed. Usually you have more sort of control points. So I'm working on that in other projects. I have other funded projects that work on that problem. It's a different challenge. Like the HVAC system is much more complicated. So sometimes it's harder to get it to do what you want it to do. These are very simple, but you need to aggregate large numbers to get a large resource. And so pros and cons.
But in those kinds of, and maybe this would apply also to the residential, but there really seems, we're all trying to figure this out, but this really, eventually, this is something that the AC hardware companies and the thermostat companies will need to be aware of, and will be building the functionality into their products moving forward. We're trying to hack it and make it do what we want it to do. Wouldn't the ideal be that they can do this?
In the thermostat, yes. Yeah. Mm-hmm.
Yeah. Okay.
Yeah. A thermostat could do everything we're doing without the need for additional hardware if you configure it properly. Well, Scott, I don't know if you disagree with that, but is that fair? Yeah.
Totally fair. I mean, to go back to the worrying about the units themselves, I think some of our very earliest meetings for this project almost 3 years ago now were hours of discussion of okay, we're going to do all this cool stuff, but how do we protect the air conditioners? Like that was like some of the very first meetings we had. Greg was part of that. And the longer we talked about it, we all sort of had to sit back and go, oh, this is going to get more complicated than we wanted, but fine, we'll do it.
Yeah, I specifically remember talking about how to protect the air conditioners, but also how to get the capability we want with whoever had open API access. And so a lot
And
of
then the list got to zero really fast.
yeah, and so
Hence
it
all the
wasn't
custom hardware.
yeah, it wasn't very much a question of whether they could do it. It was whether they would let other people do it. So
Yep.
Standards are good and bad in some ways, but honestly, kind of some structure around who can do what through a device interface, I think would be useful, but we'll see.
There's a question here from Jim, and it's an engineering question, Scott. You might want to. What about the big hammer approach when the homeowner or community has a behind the meter battery, total disconnect from the grid to shed all load, but some hybrid that allows solar to grid but no grid to home? I'm not quite sure I understand the specifics of that, but when it comes to islanded homes, would these kinds of things be, I guess, more help optimize the battery use?
They might. You'd have to make sure that you had enough resources, right? The point that Jen is making around the numbers required. For instance, in the project that we're doing, where we're actually going to be running these demonstrations this summer, we have approximately 100 folks signed up where we're actually going to be making some control actions on their air conditioners. That is only a portion of the project. We've actually got significantly more than that in simulation that we've validated through some lab testing at one of the national labs, right? So you'd have to be really sort of, I would, I like the idea. The practical implementation of that is a little bit more challenging. Like Johanna, we have other funded work. We were on a program with DOE funded work for with EPRI, where we looked at using distributed generation and demand response to help black start in the case of an outage. So there's other ways and other mechanisms that we were looking at that problem.
There were also some other questions about, I guess, different cooling technology. So whether this would transfer and apply to heat pump systems, to mini splits, to window units, to, we're kind of focused on high use areas here in Texas, but in areas that are where heating is more of a concern than cooling, would this kind of approach also work with different technologies and even with heating?
Yeah, so our approach is generic to be able to do heat. So heat pumps are basically air conditioners for, run for heat. They can run for heating and cooling, so it can do that. Any type of air conditioner with a thermostat is fine. So if it's a window box air conditioner, as long as it also has a thermostat, and it's not just one of the ones where you set to blow at a certain rate, that would work too. It works for refrigerators, electric water heaters, freezers. Like it's basically generic enough to work with any of these types of thermostatically controlled load technologies. So
right. Okay.
And the
I guess
reason
maybe
the reason we haven't focused on heat pumps is just because they're not, well, in terms of the test bed, we didn't have access to a sufficient number of heat pumps, but there just aren't as many heat pumps on the ground, right? Once we do that transition to electrification and heat pumps, this is an obvious thing we could try in northern climates as well. Yeah. And
so I wonder, maybe Greg, this might be for you, but maybe if we could kind of take a step back and talk about kind of the different players that would, let's just presume that all of this research that we're working on here has been resolved and we figured it out. There's the important role of the aggregator, and then what the aggregator does with these individual savings at millions of homes across the country, and how that has some kind of impact either on cost or on emissions or on grid stability. So I wonder maybe for the non-aggregators on the webinar, if you could maybe explain how this virtual peaker concept works, what needs to be allowed in order for it to work, and what the impact could be in either a given region or in a country or in a state.
Yeah,
And I know that was a lot. There were a lot of questions in that, but just the general idea of aggregation, what it is, how it works, and what the benefit of it is.
Yeah, so from an aggregation perspective, you have a bunch of homeowners that actually own the device that are agreeing to participate in some program. You have an aggregator who's typically the one signing these up. It could be an aggregator, it could be a utility, to basically create some benefit out of being able to coordinate these devices. So for utility, it might be peak shaving. For an aggregator, it might be market participation, where they're being paid for energy shifting, or they're being paid, in this case, for frequency regulation. They're actually bidding into a market and receiving compensation for the ability to do that. Typically, what happens is there are some incentives passed on to the homeowners or device owners who sign up for these programs, whether it's a portion of the income or a flat rate, bill rebates for utility customers, things like that, is typically how one of these program structures are set up. So you have, again, you've got this core entity, a utility or an aggregator, basically using these devices to create some benefit, whether it's peak shaving, market participation, frequency regulation, passing on those benefits to the homeowners that have signed up for this. Feel free to rehash other parts of that question if there was more to it.
So there's a comment here. I'll let Scott or Johanna add on to that, or if there's any additional comment, or I was going to move to another question. So there's a skeptic in the webinar that the approach here implies that a utility or an aggregator will require communication access to hundreds of thousands or millions of homes and devices. Any thoughts on, and I guess the alternative would be an approach that enabled the algorithm and a building controller, I don't know, I guess individual decision points and signing individual people up is I think the crux of this skepticism. So when it comes to the scalability of this and the consumer adoptability of this, do you guys have comments there?
Yeah, I can talk a little.
Assuage our concern.
I can talk a little bit about the software side of scalability. Basically, we integrate with device APIs or OEMs, the manufacturer APIs directly. And we have the ability through that to scale to a huge number of devices. And a lot of it is basically how you structure the software to directly keep that in mind of where the end goal is in terms of scale. And so that's one of the approaches that we've had at Virtual Peaker from day one is how do we build this in such a way, and how do we structure the software to carry this out in such a way where it is scalable. And so I think we've run testing and we can have like millions of hits through the API on tasks before we need to do anything. And we can extend our hardware along with that. And so from a scalability perspective, especially with cloud computing, it's really a non-issue from the software perspective if you approach it the right way.
One of the things that Pecan Street has,
Johanna, do you want to jump in there?
Oh yeah.
Well, so I would say if you can build this into the thermostat, you're not needing to build any new links, anything. And the thermostat has enough compute power together with, like, if the thermostat manufacturer or even a company like an aggregator who was working with them had access to all that information, then you could do this. So it's not actually asking for a lot of extra stuff. And then in terms of is Big Brother inside your home playing with stuff. I mean, obviously you have to have a relationship with whoever's doing this, utility, the aggregator, the thermostat company, whatever. But I imagine that would be created also, that you would buy a thermostat or sign up for the program or whatever initially. And there would be some negotiation there where you're signing a contract to participate. And through that, you could declare like how flexible you're willing to be, and like when you don't want this to happen, and when you're okay with it happening. And you can spell these things out in these sorts of agreements. I mean, the program might have several different levels, and in any case, it's not just like somebody's going to take over your house, right? And I think the reason why we focus so much on this non-disruptiveness is because if it is truly non-disruptive, you're not noticing the temperature change, your device is just cycling at slightly different times. And by the way, you don't decide when your device cycles now. There is a piece of software deciding for you when it cycles. So you don't really care if it cycles at slightly different times, so long as your house is in this range. Like, it's not actually changing your experience at all. And so if you got a bill rebate for doing this and it was no burden for you, and it didn't mean adding any extra software, hardware, communication, why not?
Right.
So,
Yeah.
Right.
Yeah. The last thing I would add is that, there's a number of models under which this is done. I'm looking at the question. It starts with approach requires utility to access. Well, odds are the utility is not going to access this. The most times I talk to a utility, you say, well, we want you to talk to X number of thousand homes. They're like, whoa, no, we don't want to have anything to do with that. We want to hire an aggregator, a virtual peaker type company, right? And we want to talk to one individual and let them handle the rest. So, and just as Johanna said, that, once you get that controls to the point where, and we've done demonstrations in the past that are more simple, peak reduction, not controls, like not more advanced load shape following controls like this, where over the course of a summer, we had like 2 opt-out events out of 75 participants and 30 demand response calls. And only twice was the opt-out button push. And one of them, I'm not sure was real, because there were other opt-out button pushes that day. So I'm wondering if a kid got a hold of the controller.
Daddy, it's hot. Yeah.
No, I honestly think, because there was
out.
enough of them, I think a little kid got a hold of it and went, the light comes on, clicky, 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 clicky.
Right. Hey, so for those of you who have been reading Pecan Street reports, there are a couple of drums that we hit often when it comes to renewable energy technology, software, hardware, and that's one of standards and protocols and open access. And that one, we understand that there are companies out there who want to own the supply chain. It's a money-making opportunity, and developing proprietary technology is certainly one way to do that. But it sounds like in this case, the more open and available the control and the data from these devices is, the better it's going to be for the broader community, and that the proprietary nature of some of these controls might actually, is or could slow down the deployment and the scalability of this. Am I oversimplifying that, or is there a point there?
I would suggest that when you said that the lack of open standards and access is slowing down deployment, yes, it is. I wouldn't say it could. I'd say it is slowing down.
Yeah, and even a structured process for getting access to it. Maybe it's not a completely open API, but having a structured process for this is available, this is how to gain access to it. That's consistent across devices would be helpful.
So Pecan Street's not really a here's an email address for you to send kind of organization, but maybe folks who are watching here could look at the name of the thermostat that they have and send a note to customer service saying they want this.
and the electric vehicles and the solar inverters and the battery inverters, and it's not, unfortunately, it's not just in the air conditioning industry. Right.
Okay. Well, guys, we're closing in on an hour, and so before I'm going to be scrolling through the chats the chat and the Q&A to see if there are any follow-ups, but I wanted to just, for each one of you, give you an opportunity if there are any, parting comments or thoughts or reactions to some of the questions. I guess anything that we want to leave people with, my recommendation is always leave them with hope and optimism. So maybe if we can refocus some of the technical stuff that we've talked about to kind of where this is going, where what we hope to resolve from the work that we're doing. And then I'll scroll through the chat and see if there are any last questions. So Scott, I'll let you kick off the final commentary.
Yeah, I think I would, I started this talking about some of the market reasons why this is and current events of why this is so critical. And I think my big overarching takeaway to sort of pivot and change a bit, what you were asking about is, I don't see this in the short medium term getting any better. I don't see any market forces. And so some solutions along these approaches could be a way out of the situation that we currently find ourselves in, where we have, likely record demand and grid stresses because of that early in June in Texas, for instance. And so the solutions that we're talking about here are a very important part of continued reliable operation in my mind.
Johanna, you're up next.
I keep changing my mind on what I want to say to this. Just in terms of, I saw some comments in the chat about we should have done this yesterday, like do this faster. Yeah. There's the do this faster comment. Why aren't we doing this now? I struggle with there's market forces, but there's also all these regulatory barriers and just not even figuring out rules. I mean, Scott talked about this in the context of ERCOT. It's not even clear how resources like this could participate in ERCOT. I think some of the other ISOs are further along. Some of them already use loads to provide frequency regulation, but still not at scale, right? Which is where our project is at. And FERC 2222 is trying to just open up the playing field for distributed energy resources in general, but I'm not sure that they call out loads as a resource nearly as much as they could versus solar and storage. And in this space, people who work on technology like I do and all of us do, that you're looking at here, we need to be involved also at that sort of regulatory policy level to actually make this stuff happen. And unfortunately, I think that's kind of the sticking point right now. That's not a happy point to end with, Colin, but a call to action. Yeah, and is it a call to action? Sorry.
To put detail on that, like some of the new rules changes that are being required by FERC, the utilities were told, please tell us when you're going to have these new rules in place. And in some places, they're like, yeah, we might have that in place by 2026, 2027. Like,
well, I'll point out the double-edged sword of this issue. One is on the political and the regulatory side. It's complicated. It is complicated, and that is not helpful. The second is that it's not a hot button issue, not a politically divisive issue, and in the current state, that's a hard thing to get attention for. And so I do think that the louder normal people can be in suggesting to their elected officials and the people who appoint the regulators, things like that, about making sure that we're making the grid and things that use the grid smarter and more capable. I think that's going to be important because it's not just going to happen. This is not something you win elections with, right? We got renewable resources and load shaving as a resource on the grid. Vote for me. I don't see that happening in a while. So, Greg, I'll let you wrap it up, and then we'll let everyone go get some lunch.
Yeah. In general, I think increasingly the technology is out there, and it's increasingly available. It's, as Johanna mentioned, a lot of the access issue, but utilities are starting to be interested in more nuanced ways of controlling devices. the ability to communicate with them is there. And that's just going to continue increasing over the years. And so a lot of the infrastructure is getting out there. And so to try and end on a positive note, we've got a lot of capabilities that are getting out there into the system to be able to leverage. And I think if we frame the conversation correctly, there is a ton of potential.
Great, awesome. I'm going to make one last plug because there were a couple of comments. I saw that Rachel with Pecan Street was put something in the chat about participating in our research. If anyone has any questions about our research, participating in it, you can email info@pecanstreet.org. If we have an answer, we'll get it to you. And if we don't, we'll tell you why we don't. But I just want to thank Johanna and Scott and Greg for joining us. Thanks all of you for joining us today. If you have any questions about this webinar, please email me at media@pecanstreet.org. And with that, we will let everyone get on with their June afternoon.